a fixed interval between these two 90-degree pulses, and we have this 180-degree pulse, which was right in the middle of this period to begin with, and moves like this as the experiment goes up. And here we don't have this feature of increasing exponential. Here is an experiment in which the signal is more or less constant type. So we have the decay has been compensated, so it has a resolution enhancement. And the omega-1 direction is, there's no J coupling, doesn't show up. The delay has to be matched to the coupling constant that you're looking at. Okay, and that is necessary, otherwise you essentially are not bringing the magnetization antiphase for the coherence transfer to take place. And there is a minimum value of delta which is equal to T1 max, that's obvious. And the cross peak intensity is dependent upon the value of J and the delta. Okay. The result of this experiment is quite good, as shown in the last transparency. And an experiment has been done by the Bombay group on oligonucleotide. They are specializing and do a lot of experiments on oligonucleotides. And one can see that it's decoupled in the omega-1 direction and not decoupled in omega-2 direction, which is very good, but one can still read the coupling constants out of it. And you can see, if you take a cross-section at one of these cross peaks, here the cross-section is shown in the lower diagram, and one can measure coupling constants out of it. And that's nowadays routinely done. In 2 pages, I have here an analysis of the scaling experiment, which I will not go through here, and anybody who's interested in can look through them and convince themselves that they work. I'm sure there are questions.
Anil, on 526, when you just talked about this this cross section,
yes,
peaks,
yes,
all of the scale. I'm just concerned about the scale. And this entire set of wiggles goes within that thing called T10 up there. You've just expanded the thing in the top circle.
Yes.
Expanded out.
Yeah, that's the cross section. See, this is a contour plot. Think of the contour plot as something which is up and down like this.
So how many peaks are we seeing in this bottom one?
Pardon me?
There are 2 on the. Are they these 4?
Oh, this one.
What's the total number of peaks down there?
Okay, there are 4 peaks. 1, 2, 3, 4. 1, 2, 3, 4. These are because plus, minus, minus, plus character.
So 4 big peaks.
It's purely absorptive.
And the other thing over there is another set of 4?
This is a carryover wiggle from a nearby peak, and most probably this one.
Carryover, that means it's on the tail or something?
And therefore, it's dangerous to look at one cross-section. One should look at a contour plot. Otherwise, you may start thinking that at this place, we have a cross peak here, which is not true.
So is COSY itself a good experiment to do? Or
okay, there has been so many attempts have been made in trying to improve COSY. All of them work, but COSY still is the first experiment and perhaps the most informative experiment. Somebody may disagree with me, but I would say you can't perhaps do away with the COSY. There is one experiment which we will talk about a little later, which could replace COSY, and in fact is so much used as a replacement for COSY that, and is a better experiment than COSY. Intensity is slightly poorer, but has fewer problems. That's called double quantum filtered COSY, and we'll talk about that. And that is actually a very good experiment. And the only close replacement to COSY is the double quantum filter COSY. Comments? Questions? Comments?